Hey everyone. So this video is going to take a look at how we can sometimes get Taylor series from Maclaurin series. So the example we're going to be taking a look at here is I want to find the Taylor series. I'm just going to call it TS, and that'll be Taylor series. That kind of looks like a 5, not an S. Hang on, there we go. S. At x equals pi for the function e to the x. So this thing that I'm showing you will work for some of the functions that you're working with, but not always because of the way the function works out when you manipulate it. So what is the Maclaurin series for this function? Remember, it's e to the x is equal to the sum of n equals 0 to infinity x to the n over n factorial. Right? If I do all this stuff, I showed this in class. If I find the nth derivative of f of 0, or sorry, the nth derivative of f evaluated at 0, then it's always just 1. So the Maclaurin series would be this. But this is not exactly what we're looking for. We're actually looking for this over here. Right? We're looking for the Taylor series. So we want something that's not like x to the n, but we want something that's like x minus, well, pi. So in this case, a is equal to pi. All right, so we start off with e to the x, because eventually we want whatever we have the series to be equal to e to the x, but the polynomials we want just have to be x minus pi, right? Because a here is pi. So what I do is I try to center my function around pi. But the thing is, e to the x is not equal to e to the x minus pi. It's e to the x minus pi plus pi. So this is the thing that I'm doing to get rid of, to actually, I guess, have me legitimately be able to do this. So here, this is equal to e to the pi, e to the x minus pi here. Right? And because this Maclaurin series is true, instead of x, I can just plug in x minus pi. And this is equal to sum of n equals 0 to infinity. Instead of x, I've got x minus pi to the n all over n factorial. And sorry, this is the e to the x minus pi, and you're probably asking, oh, where did the e to the pi go? That's my mistake. Here's e to the pi. So e to the x minus pi is equal to this thing here. E to the pi is e to the pi. So there you have it. This is actually the Taylor series for e to the x centered around x equals pi. So let's just double check that and make sure that's actually right. Remember, in the Taylor series, we're looking for f to the nth derivative of a, and in this case, a is equal to pi. So what is f of x? F of x is e to the x, like I said before. The nth derivative of x, well, no matter how many derivatives I take, it's always still e to the x. And so fn of x is equal to e to the pi. All right, now the formula for Taylor series is f of x is equal, sorry, hang on, I shouldn't say f of x, this is the Taylor series. This is equal to the sum of n equals 0 to infinity of fn at a over n factorial x minus a to the n, and we said that a was pi. So this a equals pi, this would give me the sum of n equals 0 to infinity e to the pi over n factorial times x minus pi, because a is pi, to the n. And what do we know? E to the pi times the exact same thing. So this is actually equal. So in some of the cases, like especially when you use e to the x, you'll be able to get the Taylor series from simply looking at the Maclaurin series and doing this kind of manipulation. So this is a bit of a hint for you for, what is it called? Your assignment for certain parts of it. In case you don't want to find the Taylor series of certain difficult functions. So let's take a look at another example of me doing this. It's going to be more complicated, and I'm going to want to find the Taylor series of the ln of the absolute value of 1 plus x at x equals 2. So I'm just going to say this again. This is a Taylor series. So this really just means set a equal to 2. So we're going to use the Maclaurin series to be able to do this. And if you remember, if I said in my last video, anything that we did with the manipulation of like the 1 over 1 minus x form, well, that was actually the Maclaurin series. So if you remember, so let's say we've got 1 over 1 plus x, and this was equal to 1 over 1 minus negative x, and that's just the sum n equals 0 to infinity of negative x to the n, which is this. So at this point, after working with these series for a week, these power series for a week, we hope that you would be able to identify right away that if it's a plus down here, if it's a plus here and not a minus, then the signs of your terms, your subsequent terms, will alternate, right? So you can go straight from 1 over 1 plus x all the way to this thing right here. So I've said it multiple times in class, but we're just going to start assuming that we can take that for granted. But here's the math in between to why that is true, right? So it's really the negative x to the n, and if you expand that, then I get the alternating terms. All right, so remember with the power series, how do I get from 1 over 1 plus x to this one up here? Well, I just integrate. The integral of this one, the integral of this function here will give me back ln of 1 plus x. So I'm going to say ln of 1 plus x, and that's equal to the integral of 1 over 1 plus x dx. I can go right in here and sub in the series, and this will give me the series, negative 1 to the n, x to the n, and this will be multiplied by dx. So I do this, I can bring the integral in. Negative 1 to the n does not depend on x, so I can just bring it all the way in. Or I can just go right ahead and evaluate this, and this would be the sum of n equals 0 to infinity of negative 1 to the n, because I left that alone, x to the n plus 1 over n plus 1. This is just me taking the integral. Of course, I get a plus c, and the c is just 0. Because if you set x equal to 0, what happens? This becomes 0. This becomes ln of 1, which is 0, so c is just equal to 0. So that's me just solving for the coefficient here that I get from integration, and it's just 0. All right. So now we have ln of 1 plus x, and this was this power series that we talked about last week and how we got this. But it turns out this is actually the Maclaurin series, right? It's like x to the n plus 1, right? It's x to the, it's like x minus 0. So it's actually centered around x equals 0. So what I'm going to do instead is I'm going to use this formula from the Maclaurin series to be able to get the Taylor series that I wanted originally. Remember, so I want the Taylor series, and I guess it's up there and I can't see it anymore, at a equals 2. So let's find out how we can do this. So I start off with the ln of the absolute value of 1 plus x, right? My function that I'm dealing with right now, the function I'm dealing with right now is the ln of the absolute value of 1 plus x, and I want to find this around 2. All right, so just like I did before with the e example, this would be like ln of 1 plus x minus 2, and the x minus 2 is because I want it centered around 2, but whatever I do, I have to kind of negate. So it's x minus 2 plus 2, so it's like I've really added nothing here. All right. So this is equal to the ln of 3 plus x minus 2. And basically what I want to do here is I want to make it into this form up here and have some term where I deal with something like this. It doesn't have to be x, it could be something else, but everything else looks almost identical. So I'm going to do just that. this is equal to ln of 3 times 1 plus x minus 2 over 3. And if you remember from your log rules, if you have two things multiplying each other inside the ln, well, you can split it up in terms of addition. So in math, that looks like this. Ln of AB is equal to ln of A plus ln of B, provided that both A and B are greater than 0. Hang on, just let me catch up and finish writing that. AB is greater than 0. So this is equal to the ln of, well, A is just 3 here, and B is everything else in this bracket. So ln of the absolute value of 1 plus x minus 2 over 3. And here I'm not going to scroll down because we still need to see the thing up here. This is exactly the same as, the second term here is exactly the same as ln of 1 plus x. But instead of x, I actually now have x minus 2 over 3. And so this is equal to the ln of 3 plus, and now this is now the sum, but of course everything that I saw that I see, instead of an x, I will now sub in with x minus 2 over 3. So I've got the negative 1 to the n just like before. This will be x minus 2 over 3 to the n plus 1. This whole thing will be over n plus 1. And of course there's no c, because remember we said c was 0. So I'm going to write this out a little bit neater and say this is equal to ln 3 plus the sum of n equals 0 to infinity, negative 1 to the n, over n plus 1 times 3 to the n plus 1. And this whole thing is times x minus 2 to the n plus 1. Right. So here we actually have it in the form where the terms of your polynomial will be x minus 2. So they're not just x anymore, it's now x minus 2. So you can see from this, we've actually been able to use the Maclaurin series that we had up here. So this was the Maclaurin series right here, because the polynomials are centered around 0. It's like x minus 0. And down here we've manipulated our series so that it's now x minus 2. Right? So this is now the Taylor series at a equals 2. So it's a bit of a pain for me to actually go through and try to compute the Taylor series by doing all the derivatives evaluated at a. Like I would need to use this form, and I guess it's just going back to the previous question, but it's the same form for Taylor series. I would need to use this. I would need to evaluate all the derivatives and try to come up with a general form, whereas this was a little bit easier. So you can do this for functions like, 1 over 1 minus x. And in fact, in my slides last Monday, there was an example of this, where instead I didn't center it around 0, I centered it around 4. So you do things like this, e to the x, things like ln of 1 plus x, I guess, is the one I just did. So things that look like this. So basically, you need to be able to rewrite it like this and be able to reuse your Maclaurin series to be able to do this. So this is really a hint for question 3. 3a, I've already given you a hint on. I've already used one of the functions that you have to use there. And as well, I guess for 3b, what you need to work on is coming up with relating cosine to a function where you can write like that function of x, like x minus pi over 2 or something like that. So you'd have to use one of the cosine addition formulas somehow. So basically you do the same thing, you do the same process, except after you do this step, so you'd have cos of like x minus pi over 2 plus pi over 2, and then you'd have to work out from there what that is equal to. Okay, so this is my second video. Hopefully you were able to get something out of it that you can use sometimes the Maclaurin series to come up with the Taylor series. And of course, remember, me picking like x equals 2 here is just arbitrary, right? I could have picked x equals 5 equal to pi, anything I wanted, really. So to shift it from 0 to whatever value you're looking for. Same thing up here, where we start off with e to the x. We shifted it to pi, And again, pi was completely arbitrary. I could have picked anything I wanted. So that's the idea here. This is one of the techniques you can do to find the Taylor series from the Maclaurin series. This won't work for every function, but for some of the functions I've shown here, this is how you would do it. Great. See you later.